So let's talk about composition of linear transformations. So first, a theorem. Suppose U, V, and W are vector spaces over a field F with linear transformations T going from V to W and S going from U to V. Then the composition of those maps, so T of S, we'll call it R, that composition is a linear transformation itself. And so here's the proof. Well, we have this diagram of maps and spaces. So S goes from U to V, T goes from V to W, and in green here I've written the composition T of S goes from U to W. And that composition is what I want to show is a linear transformation. So let U and U prime be vectors in U, and let C be a scalar. Then R of C U plus U prime is equal to T of S of CU plus U prime. But now since S is linear, we can break that up into T of C times S of U plus S of U prime. And now we use the fact that T is linear to break that up. And we get C times T of S of U plus T of S of U prime. But that's exactly C times R of U plus R of U prime, which shows that R is linear. Now suppose all these spaces are finite dimensional. So U is p-dimensional with basis A, V is n-dimensional with basis B, and W is m-dimensional with basis C. Then I again have this diagram of maps and spaces, S going from U to V, T going from V to W. But now I can identify, using the coordinate map, U with FP, V with Fn, and W with Fm, using the coordinate maps that we talked about. Okay, and so then I have the left multiplication by the matrix representation of S relative to A and B. That left multiplication defines a map from Fp to Fn. And similarly, left multiplication by the matrix representation T of T relative to B and C goes from Fn to Fm. The composition T of S goes from U to W. And so there's this linear map that goes from Fp to Fm that should be left multiplication by the matrix representation of T of S. And the point is that matrix multiplication is defined in such a way that T of S, its matrix representation, is the matrix representation of T times the matrix representation of S. Right. So the weird formula for matrix multiplication that we talked about in the last video, it's defined in such a way that it exactly agrees with what you would get by computing the matrix attached to the composition of linear transformations. So here's the theorem. Suppose I take three linear transformations, R, S, and T. These are all going from a vector space V to a vector space V. Then R composed with S plus T is R composed with S plus R composed with T. Composition is also associative. R composed with S and then composed with T is R composed with the composition S and T. And 3, R composed with the identity is the same as the identity composed with R, is just R. And 4, scalar multiplication behaves in this way. A times S composed with T is A times S composed with T, which is the same as S composed with A times T, and this is true for all scalars A. A corollary of this is if I take a matrix A, it's an M by N matrix, and I take a matrix B, an N by P matrix, then left translation by the product AB is equal to the composition of the linear transformation left multiplication by A composed with left multiplication by B. And so here's the point, here's the upshot of this section. It's saying for finite dimensional vector spaces, if you're willing to fix a basis, you can identify linear transformations with matrices in such a way that you're identifying composition with matrix multiplication.